Hey everybody, I am Lori Penizak, and I'm so glad that you guys can make it to the webinar. I obviously wish I could see all of you in person, but hopefully soon. So today we will be discussing identifying minerals with a field spectrometer. The outline for today's webinar has us first talking about NIR spectroscopy, following by the oreXpress advantages. We will then go into types of mineral signatures we see in the visible and the shortwave range. Interpreting mineral spectra is very important, so a general overview of how to do that will be included in today's webinar. And then to wrap things up, I will be giving a live demo of our EasyID mineral identification software at the end of the webinar. So the oreXpress is a full range UV vis NIR spectrometer that goes from 350 nanometers to 2500 nanometers and has a standard spectral resolution of 2.8, 8, and 6 nanometers. It is used in the mining industry and for various geological research applications. It's rugged and built for the field or can be used in the lab. There is no sample prep needed as the tool is non-destructive. While in the field, it goes in a backpack operated by lithium-ion batteries for approximately 8 hours worth of field work. So just as an introduction to how the oreXpress is utilized, near-infrared has made a major impact on the exploration industry because it has changed the way geologists think about their rocks and about the different alteration systems and relationships between associated minerals. Having the oreXpress at the outcrop, in the core shack, or in the open pit gives instant information about rocks that may all have similar physical appearances. It provides in situ data that allows the geologist to immediately integrate several data sets, geophysics, geochemistry, and mineralogy, where this information can be quickly applied for a better understanding of what is physically observed. Reflectant spectroscopy is changing the nomenclature of exploration and allowing geologists to look at mineral associations that provide more in-depth understanding of not only the rocks themselves, but the processes that have altered them into the resources that are important to the world. So reflectant spectroscopy, which is the type of measurement taken with the oreXpress for minerals, can be defined as the technique that uses the energy in the visible, which is 350 nanometers to 700 nanometers, in shortwave, which is also known as SWIR, which is 700 nanometers to 2500 nanometers, regions of the electromagnetic spectrum, also known as the EMS, to analyze minerals. The science and techniques of reflectant spectroscopy are based on the spectral properties of materials. So certain atoms and molecules absorb energy as a function of their atomic structures. In the visible region, this is caused by electronic transitions such as crystal field effects, charge transfer, conduction band transitions, and color center phenomenon. Much of this simply involves release of energy when an electron changes energy levels in an atom. Absorption features in the SWIR region are a function of the composition of the mineral. They are a manifestation of energy absorption within the crystal lattice from vibrational state transitions. Because these vibrational states correspond to distinct energy levels, The absorption features occur at well-defined wavelength positions. The energy levels that define these wavelengths are a function of the size of the ionic radii of the cations bonded to different molecules. So the bonds will vibrate at different wavelengths as a function of the length of the bond. Because the bond lengths between a specific atom and a molecule will be consistent, it is then possible to predict compositions and compositional changes in minerals being analyzed by the wavelength and wavelength shifts. The transitions between energy levels and compositional differences are manifested by absorption features at defined wavelengths. So the common absorption features are listed here in this table. For example, at 1400 nanometers, clays, sulfates, hydroxides, and zeolites are caused by OH and water. The absorption features occur within what's called a reflectant spectrum, with wavelength positions and distinctive profiles that can be used to identify minerals and organic phases. An example absorption spectrum is shown in this graph that has a doublet with two minima, or lowest points, of the feature. Each minimum has a distinctive wavelength, which is a function of the chemical composition. The units for the horizontal scale are in nanometers, while the vertical scale is percent reflectance. FWHM means full width at half maximum. This can be used for symmetry determinations that are related to crystallinity. The oreXpress acquires mineral spectra by using a contact probe with a built-in light source. The contact probes have a trigger button. When pressed, outputs data in approximately 3 seconds. There is no sample prep needed. We offer a standard 10 millimeter contact probe that fits perfectly in a core box or chip tray, and a 3 millimeter mini probe that has a small 3 millimeter spot size, allowing you to really focus in on key areas of your sample. The mineral spectra is displayed in our Darwin acquisition software, either on our rugged tablet or a PC laptop. All of the data is saved as an ASCII file, so you can use the data with any third-party software without any kind of data conversion. If you're in the field, the rugged tablet also attaches GPS coordinates to every measurement taken so that you can actually create an alteration map if needed. You also have access to voice notes and a camera on the tablet that runs Windows 10. For mineral identification, that signature is compared against characterized references for a validated identification. This can be done manually by using wavelength tables and overlaying references on the unknown, but the best way is to use our EasyID mineral identification software, which compares your mineral spectra to a database of references in the form of a mineral spectral library. EasyID has 3 built-in mineral libraries to match against: the USGS Mineral Library, SpecMin Mineral Library, and the GeoSpec High Resolution Mineral Library. You also have the option of creating your own mineral library to use. EasyID also has scalers that provide geochemical conditions for your sample and give an indicator of temperature or metamorphic grade. EasyID runs on a PC or on the rugged field tablet. You have the option of creating mineral presets to focus in on very specific groups of minerals that you're interested in, you know, such as clays, irons, sulfates, carbonates, etc. So I'm going to play a little video now. The oreXpress is probably one of the best tools used in the last 10 years for field reconnaissance and core logging. It operates from a backpack or from the field vehicle. It can be set up in a core shack or on an outcrop. It is versatile, it's flexible, and it provides the geologist with on-the-spot, in-situ information right at the outcrop, so there is instant identification and instant knowledge of the composition of the outcrop or drill core. Alteration types are instantly identified, mixtures are seen, zoning can be tracked, and mineral transition zones are characterized. This is a great tool for field exploration because it really cuts down on those lab costs and time. You can quickly, analyze your samples in the field. You can quickly analyze core even by contact measurements. So whether that's doing alteration mapping or looking for very key minerals that you're interested in. This is done in about 3 seconds each with only one click of that trigger. You get real-time data in the field using our rugged tablet or even in the PC while you're in the lab. Our line of field spectrometers they're rugged and they're built for those long field days. So, they're portable, they're very rugged, they're extremely fast, and of course, they're accurate. So each mineral has a distinctive spectral signature composed of several absorption features like doublets, singlets, sharp features, and broad features, which is a function of composition crystallinity, concentration, water content, and environmental considerations. So here is a table that shows some diagnostic features and types of absorption features for some common minerals. So for example, alunite has a doublet at 1400 nanometers and also at 2200 nanometers. There is an abundance of information that can be gained from the visible region of the EMS. This is one of the features that makes the oreXpress so valuable. Here are some of the cations that are recognizable by colors and corresponding minerals. Although the visible range is constrained from 350 to 700 nanometers, there is additional and complementary information in the SWIR, which is 700 to 2500 nanometers. For example, chlorites, they are more detectable in the visible range because there is less interference from other species compared to in the SWIR range, where their signal is usually lower unless chlorites are the dominant phase. The nickel cation also has diagnostic features in the visible range that can be detected in nickel laterite deposits and correlated to the ore zones. Chrome and kimberlite minerals, such as Chrome diopside and G10 garnets make spectroscopy so valuable to the identification of indicator minerals. So iron oxyhydroxides have many distinctive features that allow them to be discriminated from each other. Plot A shows the classic 3 most common iron minerals encountered in exploration: jarosite, hematite, and goethite. Stronger acidic minerals are shown in plot B. These include schwertmanite, jarosite, copiapite, cocomite, and melanterite. Rare earth elements also have very distinctive signatures in the visible range, as can be shown in the plot. Rare earth minerals such as species as bastnasite, monzonite, and xenotime. So this next table summarizes the majority of the common infrared active minerals that can be detected in the SWIR range. So for example, we're right here looking at an intrusion-related deposit, and we're looking at the SWIR active minerals, the key minerals being in bold. So all of these have very distinctive mineral signatures in the SWIR range. This next table is just a continuation of the SWIR active minerals. Whether you're looking at high or low sulfidation epithermal deposits, mesothermal, sediment-hosted gold, volcanogenic massive sulfide, and also sediment-hosted massive sulfide, they've all got very distinctive mineral assemblages that are active in the SWIR. So SWIR detects the vibrational energy of the chemical bonds between atom and molecule in the octahedral layer of a compound. This gives more flexibility in detecting amorphous materials. Therefore, it is possible to detect SiOH bonds and thus look at amorphous silicas such as opaline phases. SWIR is also very sensitive to water, which will be illustrated in a later section of the webinar. This is particularly valuable when tracking fluid migration through a deposit. Although the primary objective of the oreXpress is the identification of minerals found in different alteration systems, there is other information that can be obtained from the data and which is of great significance in the interpretation of the spectral information. These include chemical substitution, crystallinity, effects of water, paragenesis, and temperature. The ability to discern compositional differences in mineral groups that have solid solution substitution is very useful. Some examples are the carbonates, amphiboles, chlorides, illite micas, tourmaline, smectite clays, and alunites, all of which exhibit wavelength shifts with cation substitution. We will now be focusing on minerals of interest and how to interpret their mineral spectra. So the spectral plots in A are for alunites of different compositions, starting at the top from calcium to sodium to potassium to NH4. Note that the diagnostic feature ranged from 1495 nanometers for calcium to 1460 nanometers for NH4. In plot B, the diagnostic wavelength occurs in the 2330 nanometer range for magnesium chlorides, shifting to 2350 nanometers for iron chlorides. The carbonates group are in plot C, and these minerals show a significant shift with different cation compositions, ranging from top to bottom. So the very top being aragonite, the very bottom being azurite. Iron oxides, hydroxides, oxyhydroxides, and sulfates are very important not only to the precious metals exploration, but also in the determination of oxidation states and acid drainage creation potential. They can be used in the field to provide approximate pHs in an environment, especially along a stream. This illustration shows pH changes along a stream from a sulfide metal source through neutralization of acid waters by dilution and volume effects. The three most common iron minerals encountered in gold and copper deposits are jarosite, goethite, and hematite. The emission features are actually more consistent and reproducible than the absorption features. These features all have a range. These minerals are usually mixtures of each other, and therefore that wavelength range is more applicable to defining them. So the iron sulfates are very useful in helping to determine that pH of their environment and potential acid drainage factors. They are plotted in B for the visible range and C for the SWIR range, and include schwertmanite, jarosite, copiapite, coquambite, and melantorite. Except for jarosite, they show mostly water features in the SWIR. This is why an oreXpress, which has a full range of 350 to 2500 nanometers, is essential for their definitive identification. So another perspective of this shift is the aluminum substitution of illites and aluminum micas. Aluminum content of illite can be estimated from the 2200 nanometer absorption feature, which shifts relative to the percentage aluminum present. There appears to be a deposit-specific correlation in that when illite, sericite, muscovite alteration is present, there are higher amounts of aluminum apparently associated with the ore zones. So these are feature positions for a cross-section of muscovites and illites from the Speckman Mineral Library range from 2198 nanometers to 2212 nanometers. So we're looking right here. And as you can see, if you follow along the line, you can see the shift as we go from illite to muscovite. The degree of crystallinity can be determined from change in profile using a calibration data set for comparison. So note how the 2200 nanometer doublet in this kaolinite region softens and broadens from a very sharp, well-defined minimum to a shoulder as ordering decreases. So this change in profile can actually be mathematically defined and utilized as a scalar. It is a function of random and sporadic filling of metal sites in the octahedral layer of the mineral. Empty and random sites decrease order and sharpness of the profile. This plot shows decreasing crystallinity in kaolinites. So if we go from top to bottom here in this 2200 area, you can see that the crystallinity is decreasing. But also note how the water content, which is at 1900 nanometers, right, so right here, note how that water content increases with decreasing crystallinity. So a very important series is the one from montmorillonite through to muscovite. This goes through mixed layer smectite illite and illite smectite to illite. So this plot summarizes the species in the series and shows the information that can be gained by the wavelength shift, indicating changes in aluminum content. This is the most complicated series commonly worked with in alteration systems. Changes in water content, profile shape, and wavelength are all subtle between the different species in the series. They are difficult to distinguish and can only be differentiated by comparison against an accurate spectral library, which you could use our EasyID mineral identification software with the scalars to do this. So profiles also give information related to paragenesis and indirectly temperature. Broad open absorption features coupled with large water features such as those found in smectites, zeolites, and opaline silica minerals indicate ambient to low temperatures from low energy environments. As profile sharpens and becomes more well-defined, such as in muscovite, porphyrite, epidote, and dickite, the temperature of formation increases and the crystal lattice becomes ordered in a high-energy environment. So here in plot 15, this shows changes in profile as a function of ordering in the crystal lattice from broad, low-temperature smectites to high-temperature mica and porphyrite. We're looking at plot 16 here. This is showing different water sites from channel water in beryl to molecular water in gypsum to zeolite water, channel water, to interlayer water in smectites to surface water. Types of water can be tracked relative to profile and wavelength. As seen in plot 16, different types of water have different profiles which provide information about how the water was formed and where it resides. So now we will be switching over to EasyID, where I will actually give a demo on our mineral identification software. All right, so this is our EasyID mineral identification software where we do the mineral analysis. So I've selected 3 different samples for this demo. 2 types of illite and also a kaolinite mixture sample. So to our top right here, if you see my mouse, this is where our built-in mineral spectral library is. So right now we're looking in the USGS mineral library. Down here in this plot, the red spectra is the library reference spectra, and the blue is your mineral target spectra. So essentially this is matching your target spectra to a mineral library spectrum. Over here to the right, we have mineral scalars, which give very specific information about your geochemical conditions and, different temperature and metamorphic grades. So I'm going to go ahead and start with the first sample, the first illite sample. So if we look here, I'm going to zoom in on the 2200 area. So if I look in my scalar area for the ALOH feature, this is giving me a value of 2208.7. So it's correlating to the wavelength position where my ALOH is for my illite. I'm also going to be focusing in on the ISM illite spectral maturity scalar. For this specific sample, it's giving me a very high score of 3.44, which this is indicating that, this is a, higher temperature illite. So the next sample, just to show you the difference, this is the next illite sample. So I don't know if you saw it on the screen or not, but the blue line, it has shifted quite a bit to the left. So if we look at our ALOH scalar, we've got a value of 2191.4 nanometers. Now remember, our very first illite was at 2208.7. So using this ALOH scalar here really gives you information about, where your wavelength shift is occurring. So if I go back to the second one, we've got a shift to the left. We've also got a lower ISM score here. So this is indicating that we've got a low metamorphic grade illite. And this one is actually closer to the smectite illite range. Whereas if I go back to that first sample with a high illite spectral maturity, this is actually indicating that this is more on the muscovite alteration of illite. So you can really track the alteration of illites, going from smectite as the illite dehydrates into, your micas. So now I'm going to switch over to my mixture sample. So if I am looking at this illite sample, right now we're looking at the full spectrum from 350 to 2500. So the ECID is actually going to match the dominant mineral that is showing up in your sample. But a lot of you might be wondering, well, what happens if it's a mixture, if it's a mixed sample? So let's move on to that one. So if I need to figure out, well, what is causing, other minerals to absorb? I'm actually going to use our mineral preset. So I'm going to load a mineral preset that I've created, and I want to focus in on the clays and the irons only. So I just loaded that, and if you see these green sections here, these are what's called match regions. So instead of the software matching the entire spectrum for the dominant mineral, it's only going to focus in on the specific key areas to show you the, the types of minerals that you might be looking for in your deposit. So if you see my mouse down here, it's giving me for the full spectrum, the dominant mineral is kaolinite. But in match region C, which is this guy right here, it's also letting me know that I have some hematite in my sample. Now, I can also use the scalars to tell me which type of iron mineral I'm seeing as well. So if I go over here to the Fe3T scalar, so this is a very important scalar for, hydroxide type and oxide type Fe3s that you might be looking for. So hydroxide type Fe3 minerals typically have values greater than 900 nanometers, and oxide-type Fe3 minerals have values less than 900 nanometers. This scalar is used most commonly for hematite versus goethite. So if we look at our value, it's giving us a value of 884. So that's being less than 900 nanometers. I could look at this value and automatically know that this is hematite. And the EasyID software is matching that very well as well. So, as you can see, having the ability to compare your field samples to a mineral library, the various mineral scalars, and the ability to unmix your samples by loading in mineral presets, you can quickly identify and distinguish your samples. So I'm now going to switch back over to our webinar. So in conclusion, you can see that the oreXpress is a fantastic tool for exploration or research, whether it be in the field or in the lab. It adds a huge benefit being non-destructive and requiring no sample preparation. This technology allows you to identify and distinguish minerals easily. Interpreting mineral spectra using our EasyID mineral identification software allows for geologists to get on the spot in situ information about their mineral samples and a better understanding of their deposits. If you have any questions, you want to contact me directly, my email address is listed here, lori.shelton@spectralevolution.com. And make sure you follow us on LinkedIn because we do put a lot of information out there, including, the future webinars that we may be doing. So definitely give us a follow there. I hope that you have enjoyed this webinar.